Welcome to satellite communication course. Now we see that a pseudo range here. Now we know that range can be computed if we know that a time delay between the a transmitter and receiver. So we say that earlier that is about a r is equal to what difference between the timing with respect to c here. Then we can say that earlier we say that r1 that is the range between the transmitter and receiver is nothing but difference of a timing that is instant at that T2 at instant that received signal received, T1 at instant that received signal that signal transmitted from the transmitter, and that will be with respect to that C here, that we say. But in the case of a satellite navigation, all the satellite they have their automatic clock, and that a clock they have the accuracy of the clock that is of one part of 10 to the power 11. That is about the accuracy of a satellite clock. And that all the clocks in the satellite they are synchronized to a standard earth clock. Okay, so that's why that everywhere if you see that there is the same timing and all, so that's why we are able to obtain that a position. So now we can here see we can say that in general all the satellites they have the clock, and all these clocks are synchronized with the standard earth clock there. When we go for the navigation system, in that case each satellite transmits a signal, and the transmitted signal which has the information regarding the timing of a transmission and its position in the space. We supposed to we say that a satellite signal, that satellite signal has the information of a timing and information of the position. Time information at what time the signal is to be transmitted at instant, as well as the position of that satellite in the space. So that's why we can say that so that a position of that satellite at any given instant of a time it will be predictable, or it can be known with respect to that a clock timing and all, and that information of that a timing and a position, that information is called as a ephemeris data. So now in that case in the navigation system, so what is the role of a receiver? So that receiver measure its time. Okay, that timing measurement can be done with respect to the whichever the clock is present in that a receiver, in a receiver. But in the case of a receiver, that clock in the receiver it has a accuracy of one part in 10 to the power a 5. So that's why if you consider that the accuracy in terms of accuracy and the timing there, so atomic clocks are avoided in the receiver design. So that's why we need when the satellite send the signal, and that signal is received, then receiver can calculate its propagation delay of that particular signal from the satellite by taking the difference between that a transmitted signal time and a received signal time. So that will be done with a accuracy of a clock, accuracy of a receiver clock. If there is a inaccuracy in the clock, then there will be a error, and that error we can say that a offset, and that offset is nothing but to be expressed as in terms of a tau, and that offset is measured with respect to the a satellite clock, because that is about a inaccuracy. So that's why there is a that receiver clock have some particular offset, and that offset is measured in terms of a tau there with respect to the a satellite, and that offset in the clock that will result in the error in measuring the delay, or we can say that measuring this range there. So that's why while measuring the range, there will be error in the range, and that error in that range can be calculated with respect to that a clock offset. That's why if supposed to we say that R1 is equal to T1, T2 minus T1, so we can write this equation again. That is range is equal to what? There will be a T2 timing minus a T1 plus there is a offset in a clock, offset in the receiver clock. That is about a tau into AC. So here in this equation, if you see that that offset in a clock tau is added here, and if you solve it, then it will be delta difference between this T2 minus T1. We supposed to we say that we obtain the calculation, we obtain that range equation. So that's why R1 is equal to what? Difference delta T1 into a C plus a tau into C. So that is nothing but what? That is this is a part is nothing but the error. That error is measured in a delay in the range equation there, and that error is obtained with respect to that a clock offset. Okay, that is about the error we obtained. So means a range is calculated, and that range has some particular error that is about a dose. Now that's why we can modify the equation earlier we obtain for this R1, R2, R3, three transmitter, and then we supposed to be consider that there is offset. So we can write R1 is equal to under root of x1 minus xr bracket square plus y1 minus yr bracket square plus z1 minus zr bracket square plus that is about the error tau into c here. Similarly, R2 under root of x2 minus xr bracket square plus y2 minus yr bracket square plus z2 minus zr bracket square plus tau into c. Similarly, we can write the R3 x3 minus xr bracket square plus y3 minus yr bracket square plus z3 minus zr bracket square plus tau into c. These are the equations So if you see that those equations, we know that the position of the satellite x1, x2, x3, because that timing signal had the information of the position of the satellite. So x1, x2, x3 are nothing but the known factor. But in this particular equation, there are the four unknown. That four unknowns are what? XR, YR, ZR, and that's about it too. These are the four unknowns, and that four unknowns can be solved, and then we can find out the what will be the range, pseudo range equation. So to obtain this particular pseudo range equation, so we need to use a fourth satellite. Instead of a three satellite, we use a fourth satellite. Fourth satellite R4 is equal to what? X4 minus XR bracket square, Y4 minus YR bracket square, Z4 minus ZR bracket square, plus that is about a offset error. So that is about a fourth satellite. So we can obtain, we use that again a fourth satellite there. So we can obtain the range of that four satellite. Okay, with the with the help of this four satellite, then receiver can obtain that XR, YR, and ZR there. Even if there is a small error or a offset error in the clock source. So with the help of this four satellite, so that this XR, YR, and ZR is obtained there. Now this one is the principle. It is used in a satellite navigation system, and they have the different navigation system. Supposed to be, we say that a global position system, we have the a GPS, that is we say a GPS here, and then this one is about earlier it was a Navstar GPS because it was developed by the Navstar, and then this navigation system that will be developed by this US there, and then instead of in Navstar, people are saying that is about the GPS system only. Then other countries they have developed their system, and if you see that, we'll see that all those navigation system one by one. GLONOSS, that is by Russia. Then we can say that Galileo by Europe. Then we have this Baidu by China. Then IRNSS by India. This is used for the remote sensing. Okay, nowadays. Then ZQZSS by Japan. So they are about the various system that was that are used in the various countries, or they are the global positioning system that are used by the various countries, and that is useful for the navigation of the given particular object there. So now we will see that a global positioning system, that is a GPS. Now, if we say that it was developed by the Navstar GPS. Navstar is nothing but what? A navigation system with timing and ranging global positioning system. That's why you can say that it was a Navstar. Navstar. Sorry, Navstar. That is nothing but what? A navigation system with timing and ranging global positioning system. That is a Navstar GPS. And this one is Navstar GPS. Okay, Navstar, that is navigation system with timing and ranging, and GPS is about a global positioning system. And it was developed by the Defense Department of the US there in a 1973 there. So this one is used here only for the defense forces to obtain the location or a position there. So now we can say that there are some objectives behind designing the system. So now this GPS system has some objectives, and that objectives are: it will provide the position locating capability, it will provide the position locating capability, and that position looking capability to all types of aircraft, then ships, then land vehicles, spacecraft, and a satellite there. That is about the, it has a, this Navstar GPS, it will provide a position locating capability. Then it will be again useful for the a real time positioning, that is velocity and time determination capability with respect to that accuracy there. Okay, real time positioning. Then we can say that velocity and a time. Then it is to be useful for the positioning, whichever the positioning here, whichever the results in a single global geodetic datum. Then again we can write that it has the highest accuracy to defense application. So it has a resistance to intentional jamming and unintentional jamming. Then it has a redundancy to improve the system availability. Then it has a passive positioning system, and that passive positioning system that will be required one-way transmission from the satellite to the ground there. Then it will provide the service to unlimited receiver. Then that receiver is a it can be of the any simple receiver. For any simple receiver, it will provide the information regarding the position there. So in this GPS system, so if you see that, because we say that it has the information, that signal has the information of a timing. So means we can say that for the GPS system, so it will send some particular message. Okay, that GPS system will send the various message or satellite. That particular satellite send the message, and that message has a information that is about what time, is accurate time of a transmission, and their position. Now this particular message is to be transmitted by the transmitter. So it has just a message regarding what time of a transmission and the position of that satellite there. But that message is transmitted by the satellite. They doesn't know that satellite doesn't know that who is receiving the signal. Okay, means that satellite is not aware about that who is receiving that particular signal. So that's why in this GPS system, that receiver location is secure. Okay, so you can say that. And again, we can say that a receiver receiving the particular signal, and for that particular signal, that receivers are not charged for that particular message or that signal transmitted by the a satellite. So that ranging in this GPS system, they have the high speed PN codes that that messages. If you see that, and that messages regarding that, we can say that a ranging, they are using the a high speed PN codes, and again they are using the speed spectrum modulation technique for transmitting the signal there. So for the receiver, that receiving the signal from the various satellite there. Okay, so that's why you can say that, so satellite signal transmitted toward the receiver. So in that case, that whatever the receiver, okay, that receiver has some minimum number of satellites visible from their location, and then they are able to obtain the what is the position. So what are the minimum number? We have explained earlier, that is supposed to be, if we have the three satellite or a four satellite. So likewise, we need to see that that particular user is to be able to receive the signal from the minimum number of a satellite there that is required for the accuracy. So in that case, we say that the GPS system, it is highly reliable. So that's why that receiver is able to receive the signal from the minimum number of a satellite there. Again, it is a more accurate, and that accuracy with a variation of only a few parts in 10 to the power 14 hertz in a 24 hours. Because if you see that they have used a atomic clock that are used on board on a satellite, and they are synchronized with the earth clock there. Whichever the clock are present on the satellite, they are synchronized with the earth clock there. So if you see that a satellite, they will transmit, we say that is about a timing information there. We can say that they have a accuracy because of the a clock. That clock is what we can say that is about the onboard clock. They transmit the information with an accuracy, and then we can say that they have the a position again, and then position is in terms of a location, precise location. So that's why that the calculation of that particular data from this at a receiver can be done there easily. So receiver station will calculate that whatever the timing and what will be the a position location there. So if you see that a whatever the GPS receiver available on this earth now, so that receiver, they require a clock circuit, and that clock circuit is nothing but what we can use a low cost crystal oscillator and a receiver circuit. So that's why that receiver is able to obtain the position or a location at that particular place there. Only the expect that receiver expecting what they have, they have a clock or they have a circuit for receiving the signal, and then based on receiving the particular signal, then according to that signal they need to obtain that what will the position and all. So if you consider that a receiver, that receiver should have a low carrier to noise ratio, because in a GPS system they are using a speed spectrum modulation. So that's why we can say that they can support for this low carrier to noise ratio. Now we'll see that what are the various components of the GPS system. So if you see that a GPS system that has the three components, we can say that one is about a space segment, another is about a control segment, and then a user segment. Now, in the case of a space segment, what will be the number of satellites used in the space there? So generally, there are a constellation of a 32 satellites. Okay, in the case of a space segment, they have the 32 satellites. Okay, means constellation of a 32 satellites, And out of that 32 satellites, 24 satellites are operational. Okay, so means this we can say that they have the 32 satellites. Out of that, 24 satellites are operational satellites, and they are operating there. And in the case of a space segment, we say that whichever the satellites present, and they are present in the medium Earth orbit. Medium Earth orbit with a radius is equal to 26,600 kilometer from the center of the Earth. Okay, that is about a radius. And they have the orbital period, that is a T. It's about 11 hour and 38 minutes. This one we can say that orbital period. So if we consider that 11 hour means what? In a one day we say it is about a 24 hours. Which approximately we can say that a satellite period is about a half day. Okay, that is about the half sidereal day. Okay, means one particular 24 hours instead of that 12 hours there. Then we say that they have the total satellite. We say that's about a 32 satellite. Out of that, 24 satellites operational there, and they have the six orbit. Okay, all these satellites they have a six orbit at separation of 60 degree. That's separation of 60 degree at equator, means equator plane. So we have the on the satellite there are the equator plane, 60-degree separation at the equator, and each with a 55-degree inclination to the equatorial plane, and each has a 55-degree inclination, 55-degree inclination to the equatorial plane. So if you see that we say that there are the six orbits. Okay, so we can say that there are the four operational satellites in one orbit. Okay, but there are at actual there are four to five satellites in each orbit, but four satellites are actively participate in the orbit, and that satellite in the given particular orbit or in that they are unevenly spaced there in that particular orbit there. So if you consider that given orbit in the satellite, that system, that orbit are divided into a seven slot, divided into what level seven slots here, and that if you see that each satellite occupy what, four to five slots. Okay, so you can say that the spacing is designed in such a way that they will provide the phase separation of a 40 degree between that a satellite in the adjacent orbit. So means we say that we have the suppose we consider this about a Earth now. For the given Earth, we have the orbit one, orbit two, orbit three, 4, 5, likewise. That's about it. In each and every orbit, there are the satellite. So likewise, so we have the a GPS constellation. If you see that there are the given orbit, there are the number of satellites are present. Okay, so likewise, so that is about a GPS constellation system. Then GPS transmits some particular message or that data, and the data is called as a navigational data. Okay, we'll say that GPS transmitter. Now, if you see here, so that GPS transmit a navigational data at a 50 beats per second. There, I mean that is about a data, and that data transmitted by the satellite. It consists of a satellite time. That is a this one is about a data rate. We say that, and that data it has a information about that a time. Then we can say that it has a sync signal. It has a ephemeris. That is nothing but a orbital data. Ephemeris is what? A orbital data. Okay, and then we can say that it has a information about that whatever the orbital data of the other satellite. It's about orbital data means that is about what transmitted signal, and then orbital data of other satellite. So that is about we can say that a almanac. That's about a signal or information about the other signal. Again, it has a correction information, and that correction information for what? For a satellite time, then a signal transit time, sorry, signal transit time, and you can say that data on ionosphere and a telemetry data. Okay, we can say that we have the information regarding that a data there. Now, with this, we can obtain the at what instant that signal transmitted. Signal that is about we have the synchronization information, or we can say that clock information. Okay, so position of the satellite there, orbital data, and this one is about the orbital data of the other satellite there. And now then other correction information of this satellite there. Okay, so likewise. So now that particular message it transmitting at a rate of a 50 beats per second. So that is about a data is transmitted with a 50 beats, okay, 50 beats per second. So now what will be the set of message that will be transmitted by the a satellite there? So that set of message or message set, you can say that it has a 37500 bits, and that bits are requiring to transmit from the transmitter. It requires a 12.5 minutes with a data rate of 50 beats per second. Once that message is transmitted by the satellite, okay, means whatever the information is transmitted from the satellite, then what will happen? That satellite data will enable the a GPS receiver, and then GPS receiver will compute the position of the satellite and then timing transmission of the satellite. Okay, we can say that that is about the message. Then that receiver will see what will be the position of the satellite or a timing of that particular satellite from the a transmitted information. If that speed of the data, we say that a high speed or a low speed. So if you consider that a speed, so in that case generally we say that 50 bits per second. That is about the low speed data. It is transmitted, and that low speed data is transmitted using the spread spectrum technique, or you can say that direct spread spectrum direct sequence spread spectrum technique modulation by the modulator to addition with a pseudo random code at a, we can say that a PN code of what, 1.023 megabits per second, and that is nothing but what we can say that is about a known, that particular code is known as a ranging code. So we say that here for the transmitting these particular bits or that a pseudo random code, and that pseudo random code has a 1023 bits, and it has a chip rate of what, 1.023 megahertz. That is about 1.023 megabits per second. And that code, whatever the code is sending, that code will repeat at the 1 millisecond period here. So that particular PN code that is sending by the satellite, that code is called as a signature code for the satellite, and that code is different for the different satellite. So then what will happen? That receiver receive the signal from the satellite, and that receiver can identify that particular signal for the satellite, and then because that signal or that particular message is nothing but the navigation message, and that navigation message has the unique PN code, and that unique PN code will is have it has the information regarding the a satellite and all. That is about a data. That is about the data of the satellite. So now we'll see that what will be the a transmitter message of the GPS satellite, and how it will transmit the data there. Okay, that is about what will be the GPS transmitter satellite. So we'll see that a GPS satellite transmitter, okay, in next lecture.